This video will discuss how we use free body diagrams in mechanical design. If you haven't done so yet, you should read the topic reading on free body diagrams. Really, we'll very lightly summarize some of the content, but in order to understand what's going on, you really need to read those topic readings. Only takes about 20 minutes. So also in this video, we'll do some exercises. And in order to get much out of the experience, you'll definitely want to follow along with the exercises. So have a pencil and paper ready, and ideally connect up with a friend to work on the exercises together. So free body diagrams. This is a powerful tool for load analysis in mechanical systems design. It's very, very important to know how your system and all the components in it will be loaded, right? Big forces can cause things to break. Forces on moving parts can dissipate energy, and you generally need to know the forces and moments on things before you can move on to stress analysis or FEA. So free body diagrams are essential in mechanical design, and you're going to do a lot of them. So it's worth investing the time to become an expert. Now, when you're doing a free body diagram, you need a free body. And that kind of sounds obvious at first, but it's good to be explicit about it. What is inside and what is outside of the body that you are analyzing? Always be really clear about that. And you want to include only external forces, no internal forces, and ignore the small ones to keep things simple. There are some tricks to making free body diagram analysis go more smoothly. One is choosing a good free body. You want to choose a body that results ideally in one unknown that you're trying to determine through the analysis. And you can do that by picking some portion of a component or lots of components together sometimes. It's also helpful to choose a good point about which to perform moment balance. Again, trying to isolate that one variable that you don't know yet. And I know that they teach students at the beginning to draw all forces as two components and a moment, but as you become more expert, it becomes more helpful to draw your forces as vectors and your forces and moments with the sign that you expect. So they kind of point in the direction and kind of look like how big you expect them to be when the analysis is complete. That can be very useful in making things go more quickly. Now, if it's not clear yet from the topic reading and this brief introduction, I love free body diagrams. As I move through the world, when I look at a machine or a robot, I just see the free body diagrams automatically. It's overlaid like augmented reality or a scene from A Beautiful Mind. And I want you to have this too. It's a superpower in mechanical design and allows you to go through so many more candidate designs more quickly because you can quickly identify what will result in force multipliers and what won't and things like that. And you can develop this superpower too with some thought and practice. So let's do an exercise. And this is your time to call a friend. It's you got to do these exercises to really get something out of the experience. And it's always more fun to do with somebody else. All right. The Vise grip. Now this is a Vise grip. It's a hand tool that is used to amplify your hand's forces on some object that's held in the grip. And you may have analyzed these in other classes, but let's just do it quickly here to refresh. So in a moment, I'm going to ask you to pause the video, and you are going to draw a free body diagram of link 1 using the techniques that we described in the topic reading. And then you can compare notes with your exercise partner, and the whole thing should take about 5 minutes. So pause now. All right, did you come up with something good? Let's take a look at a potential answer. So here are a couple possible solutions. On the top here, we have a 2-force member. So we've said we're going to ignore any potential moment at the joints because we think it'll be small. These joints are designed to allow movement. We're going to ignore the weight of the link because that should be small compared to the forces exerted by the hands. And if we only have two forces left, then it has to be a two-force member where they point right at each other. They're collinear, equal and opposite. And we know that because if they didn't point at each other, then if you do moment balance about this point, then this force has lever arm, right? It will cause that thing to spin. And then you would need a reaction moment. And we've assumed that there are no reaction moments. All right, so this is one possible solution. If you had a different answer, check that static equilibrium is possible. Now we're going to do the same thing for link 2. So you pause the video, sketch a free body diagram, discuss it with your partner, then start the video game. And this whole thing should take about 5 minutes. All right, pause the video now. Finished? Okay, so here's an example of a good answer. We know F1 because the force of link 2 on link 1 must be equal and opposite to the force of link 1 on link 2. So that we've solved already from our previous free body diagram. This is one example of working along the chain to make the future free body diagrams simpler and resolve indeterminacy. Then we've got this force from the fingers, and here we've modeled it as a single point force directed normal to the handle. And there are a few assumptions there to pull out. So why normal to the handle? Well, it could be that there's a component of force along the surface there, but people tend to not like that. It's uncomfortable, and these things are designed to be gripped with that normal force. So let's assume that most of the force is orthogonal to the handle. You may have indicated this as a distributed force. And you've seen in some other classes that those distributed loads can be helpful for understanding, say, deformation of a beam. And that's really useful in civil engineering things. But here, if say we're interested in figuring out what this unknown force is here at the next link, then Newton tells us it doesn't matter how this force is distributed as long as we get the total force, the integral of the force applied at the center of pressure. We'll have an equivalent effect on this if we treat it as a rigid body. So that's how we get to this assumption. And those distributed loads, they can make the analysis a little more annoying. Okay, so now we've got these two forces. We know we have some force over here from the next link. Well, because these two forces both point at this point, O, if we do a moment balance about that point, we can see quickly that this last force has to point at the same location as well, at the intersection of the first two forces. We know that because if this F2 did not point at that intersection, say it pointed up like this, then if you do moment balance there, you'd have an unbalanced moment, right? The whole thing would be spinning, would be accelerating. So this is a case of what's known as a three-force member. And where a two-force member, both forces are collinear and equal and opposite. In a three-force member, all three forces point at the same location. They almost intersect at the same point. And if you had something different, a quick check that could help identify an issue would be to say, is static equilibrium possible with the forces moments that we've put on the page? Now, if you're interested in practicing this kind of thing more, you could do a free body diagram analysis of this third link and this fourth link. And that'll give you another chance to identify some three-force members and make reasonable assumptions about what the forces from that ring or from the hand are on the link. All right, so that's how we handle those textbook problems that you are accustomed to seeing. And many times in mechanical design, our free body diagrams will work out like that. But sometimes they won't, because we're designing custom systems and they're complicated, and they often don't have that neat pattern. And one of the most common issues that people run into is a statically indeterminate free body diagram. And we go into this in the topic reading a bit. But the basic idea is that you have more unknown forces and moments than you have equations. And so just from those equations, you can't tell which of the infinite possible solutions is what is going to happen in the real system. And when you run into that situation, the best thing to do is to try making some simplifying assumptions, load, and then test them using static equilibrium, deformation, and CAD sketch finite element analyses. So we'll walk through an example of what that looks like here with the T. So another exercise, make sure you got a partner on call or on the phone. So here is a component shaped like a T. There is a force applied downwards at this bottom hole. And then there's these 3 holes that are fitting onto pegs. So there's a peg inside each hole, and the pegs are connected to this square thing in the background. And that's rigidly connected to the ground. But we want to draw a free body diagram of this T component that's interacting with those 3 pegs and with this force at the bottom. So in a moment, I'll ask you to pause the video. You'll draw a few candidate free body diagrams of the T independently, then discuss them with your partner, and then come back. The whole thing should take about 7 minutes. All right, so now pause the video. All right, how'd that go? A little messier this time, eh? Okay, so here is one example free body diagram. And here again, we've assumed no moments at these holes, just a peg in a hole. Maybe the friction is low, then there's no moment. We've assumed that the weight of the thing is small compared to the force that was applied. But still, at each of those pegs, we can have 2 components of force because the holes will not be able to move, translate x in the x direction or y direction. And so there can be a reaction force. So we have 6 unknowns, and we only have 3 equations. The 3 equations will be some of the forces in the x direction and y direction are both 0, and the sum of the moments about the z direction is 0. So what are we going to do? Make some simplifying assumptions. So the next thing I want you to do is take a moment and pause the video, and I just want you to think about what simplifying assumptions you might make. Candidate simplifying assumptions that will allow you to get that number of unknowns small enough that you can answer the question of what are the reaction forces, okay? So take about 2 minutes and think that through, all right? Pause the video. All right, you have some ideas? Okay, well, let's go through some ideas that I came up with. And here's one. Let's say that we assume that, I know I need a force in the vertical direction to react out this force applied at the bottom. So why don't I assume all the force is reacted out on the right-hand peg. So this is F down and that's F up. Is this a good assumption? Well, the first check that we use is a check of static equilibrium. And so let's test this for static equilibrium. Is it possible? So the sum of the forces in the x direction, will that be 0? There's nothing. Sum of forces in the y direction, F minus F, that's 0. So far, so good. But when we perform our sum of the moment calculation about any point, but let's say we pick this point because then this force will be canceled and it makes it easier. We'll see that the sum of the forces is 0 times this force, okay, nothing, plus d times that force, that's something. And that's not equal to 0 in general, unless both forces are 0. So we can't get moment balance, and therefore this is not a possible solution for our free body diagram. Okay, well, what if instead we assume that, I need a vertical force, all that vertical force is on the middle hole, and we've got these 2 horizontal forces that are equal and opposite. Is this a possible correct answer to our free body diagram? Well, let's use our first check. And the first check is static equilibrium. And hey, the sum of the forces in the y direction, F minus F, is 0. We're good. The sum of forces in the x direction is Fx minus Fx. That's also 0. And the sum of the moments, let's take the sum of the moments about this point in the middle. We'll do that because all the forces go through that point, so none of them have any lever arm. So the moment caused by each of those forces is F times 0. So that's 0. So we've got it, folks. Static equilibrium is possible. But I'm not so sure about this yet. So let's move on to our next test. And the next test is to think about deformation. How would the component deform when you apply these forces? And I find that the best way to do this is think about it in your mind's eye. Imagine that the component was made of rubber, really compliant polymer, and how would it stretch if you applied these forces? What would that shape look like? And is that consistent with the constraints on the system? So take a moment and pause the video and try to imagine how this shape would deform applied when those forces are applied. And it should take maybe 1 minute to do that. All right, you have a picture in mind's eye. This is the picture that I come up with. So if there's a force pulling downwards, this thing is going to stretch, and the dotted lines here are supposed to be the undeformed shape, and the solid, the deformed shape. And this is okay. That force seemed to be applied in space, and so that could move, and that's all right. But this part is a little worrying. So we've got those X forces pulling the hole sideways, but we said that these were on pegs, and the peg wouldn't be able to just move arbitrarily, right? And so this deformation violates our expectation about how the part is constrained. And so it wouldn't be able to actually stretch as necessary to match the forces applied. So at this point, we can reject our idea of big horizontal forces on those holes. So let's look at another simplifying assumption. So here are a couple of different assumed free body diagrams that simplify things in similar ways. So in the left-hand case, we say, all right, let's say there's no X force on those side holes, and what the heck, there's no Y force either. The whole thing is reacted out on that middle hole. And on the right-hand side, we say, well, we've got 3 holes and this one force down, so maybe 1/3 of the force is reacting out at each hole. And this might be something that you came up with in your own sketches, if you're like many students who've taken this class before. So what about these? Is one of these a good assumption? Is one better than the other? Let's see. So our first check, remember, is static equilibrium. Can we achieve static equilibrium in these FBDs? So take just a moment and do a quick calculation in your mind and satisfy yourself that you have a firm answer to that question. And pause if you need to before we move on. Is static equilibrium possible in these 2 cases? Okay, the answer is yes. So in this case, there are no X forces, that's simple. We have F up and down, that's sums to 0. And if we take the sum of the moments about one of these points, we'll see there's no moment, and so that's 0, so good. And the same thing is true for this case. So the middle forces, excuse me, the sum of forces in the X direction is 0 again. The sum of the forces in the Y direction is 3 times this 1/3 F minus this downwards F, so that's 0. And then if we look at the sum of the moments about, say, the center hole, the center forces will drop out again. We'll have 1/3 F times some displacement minus 1/3 F times that same displacement, assuming this thing is symmetric. And so we have static equilibrium. All right, so there's plausible so far. Our next check is deformation. So now take a moment, imagine the thing is made from rubber, and picture in your mind's eye, how would it deform? And you might even sketch some things out. So I'm going to ask you to pause the video and do that for a minute or 2 and really come up with a firm answer as to how you imagine, how you picture this thing deforming with those forces applied. All right, pause the video. Okay, you have an idea, maybe a sketch and an image in your mind of how these things are going to deform. Well, here's the image that I get. So in this left-hand case, we just have the middle part under axial tension. So it elongates, and that's okay. As we talked before, that bottom point looks like it can move in this scenario. But the right-hand side, we have something funny going on. So there's a force upward on these arms. And it's kind of like a beam in cantilever bending. And bending means it's going to curve. And so this side would curve up, this side would curve up. And again, we have that problem where these holes are supposed to be on pegs, which would prevent them from bending up that way relative to the center hole. And so it looks like that set of assumptions isn't consistent with the different deformation check. Now, maybe your intuition about these things is still developing, or maybe your picture of how it deformed just looks really different from mine. So you can check if you're not sure using a CAD sketch and performing FEA. So, and we'll have a walkthrough of FEA in the next set of videos. But the basic idea is you just take something into CAD, whip it up, and do the very simplest finite element analysis you can, not getting any of the values right or anything, just getting a qualitative picture of the shape to get a qualitative understanding of how it deforms and where the forces are big. So let's take a look at, I did that, and here's the answer I got. So we've got this T shape, we put some holes in, you can see the dimensions are a little different, that's okay. And then we just fix the insides of these holes and apply a force downwards at that center bottom hole. And this pattern here is a pattern of stress. Dark blue means very low stress. And as you get more towards red, you get higher and higher stress. So the middle part here is stressed. You can see it's elongated. The deformation scale is pretty big, so that it's exaggerating how it deforms under this load. And this picture looks a lot like that left-hand case, where we just have the reaction force at the center hole. All the stress you can see is being reacted out in the center hole. Well, what if we fix it with bearings instead of fixing the inside of the holes? And we'll get into some of these things again when we talk about FEA. You get a very similar result. It's true there's a little bit of bending happening up here, but almost all the force is going towards that center hole. Now, maybe say, yes, if those holes are really fixed in space, that's like having the pegs be infinitely stiff. And this is all about deformation. So what if the pegs can move a little bit too? Well, if we model the pegs in an assembly analysis, now we've got the pegs modeled as rigid bodies, or actually not rigid bodies, but as deformable bodies in this FEA as well. Still, we see most of that force goes to the center peg. So we've verified that just thinking about the way the shape deforms can often make an accurate prediction about whether your assumptions about the free body diagram are correct. Now, the purpose of this is not to say that every time you have three holes, only the middle hole sees force, right? It's that when you have indeterminacy, deformation is what tells you where the forces are, and often you can make a simple assumption that's consistent with that deformation. So what if we changed the T? How could we get those forces to be more evenly distributed? Well, one way to do it is to make the supports even more compliant, so that the pegs, if the pegs are really squishy compared to the T, then the T can displace quite a bit, and it can bend up a little bit, and still get pretty big forces in the vertical direction at each of those points. Or if we maybe make the connection between that bottom center hole and the top right and left holes stiffer, So here's an example of a case where we've put these holes on very springy supports. I think it's maybe a centimeter of deflection there. And if those pegs are super springy, then now you get closer to that 1/3 force upwards at each hole solution. And here's another version where we've filled in this material so that it's like one big plate, and you can see that, yeah, you have lines of stress going from the center hole at the bottom to all 3 holes at the top. And it will turn out that we have really similar to the 1/3 F up solution in this case too. Okay, so the summary of this exercise is that when you run into static indeterminacy, which you will run into as you start designing your own components, use static equilibrium. First, make some simplifying assumption, then use static equilibrium to test it, then deformation analysis, then quick up sketches in CAD. And you do that iteratively and sort of prototyping your analysis to better understand how the part is actually loaded. It's very helpful. All right, the next video will be on stress analysis and design.